So far, we have been examining problems in Can you just stop it? You just stop and restart, because I had a blue pen, so that will disturb your video.
Yes, sir.
Just tell me when you're ready to start.
Ready, sir?
Yeah.
Sir, you can start.
So far, we have been examining problems in unidirectional transport, that is, transport in one spatial direction and in time, okay, for general unsteady problems. We had derived the conservation equation for general unsteady problems, and the conservation equation for the temperature field, for example, was of the form partial T by partial T is equal to partial by partial Z of alpha times partial T by partial Z, where alpha is the thermal diffusivity and Z is the spatial coordinate, T is time, and capital T is temperature. And in general, you could also have an energy source by rho Cp, okay, in general. The problems that we have solved so far are problems in which there was no time variation. If you recall, we did conduction in slabs, in a combination of slabs with sources inside in the case of momentum transfer or heat transfer or reactions and so on. But all of those were steady state problems. Okay? There was no time dependence. In this lecture, we will start looking at the simplest problem where there is time dependence. Okay? And the problem is as follows. You have a surface, okay, and let us put a coordinate system here. This is the z direction, okay, and this is a fluid. Okay, this is a fluid, okay, and the temperature is T infinity, far from the surface. Okay, the temperature of the fluid is T infinity, far from the surface, and initially for T less than 0, the temperature is uniform everywhere. Okay. And at the initial time T is equal to 0, okay, the temperature is increased instantaneously to some value T is equal to T naught at Z is equal to 0. At the surface, the temperature is instantaneously increased to the value T is equal to T naught. Okay. And so, if I plot the temperature as a function of time, for example, function of time, if I plot the temperature at the surface, right. So, I will plot the temperature at Z is equal to 0. For T less than 0, it is just equal to T for T less than 0, it is equal to some value, okay, T infinity, and at T is equal to 0, there is an instantaneous increase in the temperature to the value T naught. And obviously, when the temperature increases, the temperature of the surface is higher than the temperature in the fluid, and therefore, there will be heat conduction from the surface into the fluid. And we would like to know what is the temperature profile as a function of time, okay, in this case. And for the moment, we will assume that the fluid is has a constant diffusivity, and there are no sources or sinks within the fluid. Okay. And therefore, this source term is equal to 0, and I am solving the problem partial T by partial T is equal to alpha times d square T by dz square. The partials, because the temperature is now a function of both position and time. Okay. The temperature is a function of both position and time. And the boundary conditions, so this is the equation, and the boundary conditions are okay, T is equal to T naught at Z is equal to 0. That is, at the surface, the temperature T is equal to T naught. Okay. T is equal to T infinity for z going to infinity, that is very far from the surface, the temperature is equal to T infinity. And at T is equal to 0, T is equal to T infinity at T is equal to 0 for z greater than 0. Okay. At the initial time T is equal to 0, the heating is switched on and the temperature of the surface instantaneously increases to T naught. So, I made a however, the fluid is still at the same temperature T infinity, right. You switched on the heating on the surface, but the fluid is still at the temperature T infinity. Okay. So, T is equal to T infinity at 0 time for z greater than 0. So, these are the boundary conditions at z is equal to 0, z going to infinity, and the initial condition throughout the domain at initial time the temperature is T infinity and you have just switched on the heater. So, that T is equal to T naught at the surface itself. So, it convenient to define a scaled temperature in such a way that the scaled temperature is 0 far away, okay, and the scaled temperature is 1 at the surface. Okay. You can do that by defining T star is equal to T minus T infinity by T naught minus T infinity, okay. Okay, which implies that when T is equal to T naught, this T star is equal to 1. Okay. When T is equal to T naught, T star is equal to 1. Okay. When T is equal to T naught, this T star is equal to 1. When T is equal to T infinity, T star is equal to 0. Okay. And you can express the conservation equation in terms of T star. Since the left and right sides are both linear in temperature, you can divide throughout by T minus T infinity and you will get the equation partial T star by partial T is equal to alpha times partial square T star by partial z square. Okay. So, that is the equation in terms of T star, and these are the boundary conditions in terms of T star and the initial condition in terms of T star. So, we scale the temperature. Now, how do we scale the distance, okay, in this case? The boundary conditions are applied. One is at z is equal to 0, the second one is at z going to infinity. So, there is no intrinsic length scale in the problem. Okay. The boundaries are not specified at fixed locations. One is specified at the surface itself, which is z is equal to 0. The other is specified as z goes to infinity. Okay. So, because of that, there is no length scale in the problem. The only dimensional parameters that I have are okay, the only dimensional parameters that I have after I have scaled the temperature. The temperature has now become dimensionless, and after I have scaled the temperature, the only dimensional parameters I have are the coordinate z, time t, and the thermal diffusivity alpha. Okay. And out of these I can get only one dimensionless group. Okay. Out of these I can get only one dimensionless group, and that dimensionless group is z by root of alpha t. Okay. Okay, since there is no length scale in the problem, I have to scale the length by a combination of the diffusivity and time. That is the only way I can get a dimensionless length. Okay. If there was a finite length at which the temperature was fixed, then I could not have done this. Okay. In this particular case, because there is no length in the problem, I get only one dimensionless group, which is a combination of the distance, the thermal diffusivity, and time. Okay. And this is a similarity variable. Okay. I will call it as psi. Okay. This is a similarity variable, which is a dimensionless combination of length, time, and diffusivity. Okay. And if I can express my equations entirely in terms of psi and my boundary conditions entirely in terms of psi, then I will have effectively converted the equations and the boundary conditions into equations in terms of only one parameter z by root alpha t or psi, okay. And therefore, I would have converted my partial differential equation into an ordinary differential equation, and then I know how to solve the problem. Okay. In general, for a partial differential equation, there is no predetermined solution procedure. The solution procedure I told you in the beginning of this course. The solution procedure in general depends upon the physics of the problem. In this particular case, since I have an infinite domain with no length scale in the problem, I can reduce it to a similarity variable. And if after reducing it to a similarity variable, the equation for the temperature and the boundary conditions can both be expressed in terms of that similarity variable alone, then I will have a one-dimensional problem, okay, which can be solved. So, can everything be expressed in terms of this similarity variable? Which is a combination of spatial position and time. Okay. To do that, I have to express, okay, the derivatives on the left and the right sides, okay, in terms of derivatives with respect to psi using chain rule for differentiation, substitute that into the equation and then see what is the equation that results in terms of the similarity variable. And I have to do the same thing for the boundary conditions as well. Okay. So, let us start with that. Okay. Partial t by partial z is equal to partial psi by partial z into partial t by partial psi. If I use a chain rule for differentiating in differentiation, okay, this is equal to, okay, partial psi by partial z. Psi is equal to z by root alpha t. Okay. So, partial psi by partial z is 1 over root of alpha t, partial t by partial psi. Okay. The second derivative, okay, partial square t by partial z square is equal to d by dz of 1 over root alpha t partial t by partial psi. Okay. And since t and z are independent coordinates, since t and z are independent coordinates, I can take this as 1 over root alpha t, okay, partial by partial z of partial t by partial psi. There should be non-dimensional temperature in all of these equations, so kindly correct that. Okay. And this is equal to 1 by alpha t partial alpha t, no, alpha time, partial square t by partial z square. Okay. And since we are postulating that these derivatives are functions only of psi, that is t star is only a function of psi, what I have here is not a partial derivative, but rather a total derivative. Okay. If I postulate that these are only functions of psi, then I have total derivatives here. This is partial. And over here I will have d square. Okay. And then I also have a time derivative. Okay, I also have a time derivative. Okay, so partial t star, okay, by partial t is equal to partial psi by partial t d t star by d psi. Okay. Psi is equal to z by root alpha t. Okay, the derivative of 1 over root t. Okay, 1 t power minus half. The derivative of that will be half into t power minus 3 by 2. Okay. So, this will be equal to minus 1 by 2 t power 3 by 2 1 by root alpha. Okay. So, psi was z by root alpha times t power half. The derivative of t power half is minus half t power 3 by 2. Okay. That is this first term here times z by root alpha. Okay. And I can re-express z in terms of psi. Okay. Z is equal to psi root of alpha t. Okay. So, if I substitute that in here, I will get minus 1 by 2 t. Okay. So, dt by d psi. So, this is the left side of the conservation equation. This is the left side of the conservation equation, and the right side is alpha times d square t by dz square. Okay. I made a mistake here again, it should be psi. Okay. So, I substitute that into the conservation equation, and the equation will change to, okay, so I will write that here. Okay. Partial t by partial t minus psi by 2 t dt by d psi is equal to alpha into d square t by dz square into 1 over alpha t d square t by d psi square. So, the left side partial t by partial t is equal to alpha times the second derivative with respect to z. Okay. So, I have just substituted the expressions for those, and you can see alpha and alpha cancels out, t and t cancels out, and the final equation is minus psi by 2 dt by d psi is equal to d square t by d psi square. And as expected, the final equation, the conservation equation, is only a function of psi. Okay. It is only a function of psi. It does not depend independently on z, t or alpha. It depends, it is only a function of psi, okay, only a function of the similarity solution. Okay. And then I had the boundary conditions. Okay. The boundary conditions, okay, t star is equal to 1 at z is equal to 0. Okay. T star is equal to 1 at z is equal to 0. You recall that t is equal to t naught, and I expressed t star as t minus t infinity by t naught minus t infinity. So, at z is equal to 0, if t is equal to t naught, then t star is equal to 1. Okay. That is this condition here. And when z is expressed in terms of psi, psi is equal to z by root alpha t. So, this corresponds to psi is equal to 0. Okay. Then t star is equal to 0 for z going to infinity. Okay. When z becomes large, the temperature is the fluid temperature, T infinity, and therefore, T star, which is T minus T infinity by T naught minus T infinity, has to be 0, far away, and this is at psi going to infinity, okay, because psi is z by root alpha t. Okay. So, as psi goes to infinity far from the surface, T star has to be 0. And the third boundary condition is that T star is equal to 0 at t is equal to 0 for all z. Okay. That is the initial condition. Initially, t is equal to t infinity everywhere. okay, for all z greater than 0. Okay. At the surface itself you have instantaneously increased the T star to 1, but everywhere in the fluid T star is equal to 0. Okay. For z greater than 0 and T equal to 0, this ratio implies that psi is equal to z by root alpha t goes to infinity. Okay. So, psi goes to infinity at t is equal to 0 as well. Okay. Recall that the original problem that we had was a first order differential equation in time and a second order differential equation in z, and for that we needed two boundary conditions and one initial condition. Okay, one condition at t equals 0 and two conditions at the boundaries z is equal to 0 and z going to infinity. When we reduced two variables to 1, the equation became a second order equation for psi. Okay. The equation became a second order equation for psi. Okay. In this case you can have only two conditions in the psi coordinate. Okay. And as expected, two of the conditions for z going to infinity and for t is equal to 0 reduce to the same condition when expressed in terms of psi. Okay. The conditions for z going to infinity and t is equal to 0 reduce to the same condition when expressed in terms of psi, and therefore we have only two conditions remaining, one at psi equal to 0, the other at psi going to infinity. And this condition has to be satisfied, okay, if we are to get a similarity solution. Both the governing equation as well as the boundary conditions should be functions of psi alone, okay, if we have to get a similarity solution. In this case we had postulated that psi is equal to the similarity variable psi is equal to z by root alpha t, and then we were able to get an ordinary differential equation for psi, second order equation, and an equation and the boundary conditions, two boundary conditions as required for solving a second order equation. Because the equations depend only on psi, boundary conditions depend only on psi, therefore the solution also depends only on psi. Okay. And therefore, this similarity transform gives you a solution in terms of the similarity variable. So, let us see how we solve this. Okay. You can see that there is a second derivative on the right side and a first derivative on the left side in this equation. Therefore, I can define a new parameter which is dt by d psi. Okay. And if you define it that way, this becomes minus psi by 2 into w is equal to dw by d psi. Okay. That is what the equation reduces to. I can integrate this, okay, minus psi d psi by 2 is equal to dw by w. Okay. And multiplying throughout left and right sides by d psi and dividing throughout by w, and the solution is log of, it is always a natural log, ln of w is equal to minus psi square by 2 plus a constant a, okay, psi square by 4, I am sorry. Integral of psi by 2 is psi square by 4. Okay. So, minus psi d psi by 2, if you integrate it you get minus psi square by 4. Okay. And if I exponentiate on both sides, I will get that w is equal to some constant c times e power minus psi square by 4. Okay. And this is equal to dt by d psi. Okay. Note that w is equal to dt by d psi. And I cannot integrate this further, so I will just leave it as a definite integral. The integral of this is going to be t star is equal to c times integral 0 to psi d psi prime e power minus psi prime square by 4 plus some constant d. Okay. where the constants of integration had to be determined from the boundary condition. Okay. The boundary conditions at psi is equal to 0, t star is equal to 1. Okay. At psi is equal to 0, you can see that this integral is an integral between 0 and 0. Okay. So, the integral itself is 0, okay, but t star has to be 1. So, this implies that d is equal to 1. Okay. And as psi goes to infinity, t star is equal to 0, which implies that 1 plus c integral 0 to infinity d psi prime e power minus psi prime square by 4, this has to be equal to 0. Okay. Therefore, c has to be equal to minus 1 over this integral. Okay. I will not go into the details of how you evaluate this integral. Okay. I will not go into the details of how this integral is evaluated. All I will say is that this integral has a definite value. Okay. It has a definite value, integral 0 to infinity. This is equal to 0 to infinity d psi prime e power minus psi prime square by 4 is equal to square root of pi. Okay. And therefore, which implies that c is equal to minus 1 by root pi. Okay. And with that, I get the final solution, t star is equal to 1 minus 1 by root pi integral 0 to infinity d psi prime e power minus psi prime square by 4. Okay. Sorry, this is from 0 to psi. Psi prime is the dummy variable of integration. Okay. It is the dummy variable of integration. Okay. This is usually expressed in terms of a special function. Okay. It is called an error function. Okay. The error function is defined as integral 0 to infinity d psi prime e power minus psi prime square by 4 is equal to root pi into error function of psi by 2. Okay. It is usually expressed in terms of a function called the error function. Okay. And in terms of this error function, I get a final expression for the temperature. T star is equal to 1 minus error function of psi by 2. So, that is the final expression for the temperature field in terms of this similarity solution. Okay. Or I can alternatively write this as 1 minus error function of z by 2 root alpha t. Okay. That is the final solution for this temperature field in terms of z and t. Okay. This error function is a function. Okay. If I plot psi versus error function of psi, okay, it increases, it is 0 at 0. Okay. The error function, as I said, is proportional to, this is integral 0 to, I am sorry, this upper limit should be psi, please note that. It is the integral from 0 to psi of d psi prime e power minus psi prime square by 4. Okay. And therefore, at psi is equal to 0, this is equal to 0. Okay. At psi is equal to 0, this is equal to 0. And as psi goes to infinity, this function increases to a value of 1. Okay. This function increases to a value of 1. Okay. It asymptotically reaches 1 as z goes to infinity. Okay. And the slope of this function at z is equal to 0, okay, d by d psi of error function of psi by 2, okay, at psi is equal to 0 is equal to 1 over root pi. Okay. It is 0 at 0, it has slope of 1 over root pi, and as z goes to infinity it increases and asymptotically reaches 1 as z goes to infinity. Okay. So, that is the solution for the temperature field. Okay. So far I have calculated the temperature field, now I need to calculate the flux. How does the flux vary with position and time? I will continue that in the next lecture. I will see you then.